or at least intelligence, and it puts everything on a sliding scale. Um, so personally, I'm okay with that very ambiguous definition of computer because I prefer to think of things on like a more analog scale and not in discrete time steps, if that makes any sense to anyone else.
I think it makes a ton of sense. And that was all of it was a little bit tongue in cheek because I knew you're sitting here listening, and you have already proposed that a rock is a computer. But I kind of wanted to get other people's reaction now that you've defended the position. Did people find themselves nodding along and agreeing with me when I initially said a rock? Come on, nobody would call that a computer. Right. So my dirty secret is I think that according to some definitions, a rock is certainly a computer, as is pretty much any physical system. And so it depends on your definition.
Well, I think there's also a funny direction to think about it, right? Because I agree with you completely, right? These rocks certainly don't fill our intuitive definition of what a computer is. But funny enough, the Intel chip, I would argue that all computers are rocks. In that when we think about the Intel chip itself, it is literally a piece of silicon rock, right? That's how we build them. It's just a very carefully designed rock.
Right, which makes this whole analog digital thing get very fuzzy, right? Because, our neural network that we're designing, well, they're running on circuits and they're running on, the same exact kind of circuits, for example, that have done all digital computing, and they're designed to be digital in some ways, right? And so there's no sense in which our neural networks are really doing any sort of parallel distributed or any of that stuff. It's because it's all happening in a simulation. But, your point is that it's all physical in the end. It's all analog. Right? Even the computer is running in analog. It's running on electricity. It's running in physical stuff. There's no real boundary here that's ever meaningful. I think even the most extreme version of digital computing.
I'm a posit that a computer is not a physical system, but rather essentially a state machine that's a set of rules, a set of inputs and a set of outputs, and a function that goes from those two, and that there are physical instantiations of computers.
So the physical computer is not the thing, right? It's simply instantiating.
And if you will, a rock in that case to a human is the trivial computer. Input anything, output nothing.
So how is that different than just a function itself? So a function is, as a mapping between inputs and outputs. And you're saying that anything that instantiates a function, so namely it can carry out some algorithm, right, to produce the function, you'd say that's it. That's the computer. The computer, or rather not that's not it. That's just an instantiation of the function. How is the function different than a computer then? Because there's a series of steps, but don't you need a series of steps within some computing system, some even, I guess you could say, physically represented system? Otherwise, what's the difference?
I usually say a computer has state.
But doesn't state have to, ultimately, don't you have to ground it then in some physical state?
No.
Okay.
State is a mathematical abstract concept, right? Let x equal 10. Where is x?
Well, but state of, okay, so you're saying you can define a fully abstracted representation of a symbolic or of an algorithm.
Yeah.
Well, one thing I think worth mentioning is this idea of a virtual machine that, in your mind right now, you can picture contraptions. You can picture all kinds of contraptions. You can picture whole factories of workers and all this stuff. And so if you're very careful and deliberate about your thinking, you can picture any sort of something operating. And that's sort of this idea is that you can build machines out of ideas.
So is it equivalent to something like the program in a Turing machine, which is just represented numerically, and it could run in any, I guess the Turing machine itself is in some ways just an abstraction. It doesn't have, but it ends up being grounded. It ends up being grounded in some terms, like at least in the spatial. There's a spatial extent of a tape, for example. There's a moving left and right. So there's some sort of process that I think always ends up being represented either in space or time at the very least. So these are still kind of only, you still end up having to ground it in some physics concepts. It's not purely mathematical.
Can I jump in here a little bit?
Yes.
Because philosophers have written a lot on this subject. Specifically, they've written a lot on the subject of what is a computation. And I completely agree, by the way, that it's very hard to define what a computer is. And that Rachel's point, I think, is very well taken. It may be the only way we can do it, and then have different subsets of computer types. But I just want to point out one important distinction that we should bear in mind. And I think a lot of people don't appreciate it. So if you start with the idea that a computer is a program or a set of rules, you move from something which seems, at least at first blush, to be a physical thing to something which is instead abstract, right? Like an equation. Okay, now philosophers of mathematics, I mean, this is a field, very rich field, point out that programs like mathematical entities are abstract entities. They're not concrete. They're not physically located anywhere. So if we make that slippage, we then move in the direction of some weird metaphysics. Okay.
Yeah, so who takes that position? I mean, let's go back and say it has to be instantiated at the very least as somebody's got to write it down. And how do they write it down? Using symbolically, using some description. Where does it exist outside of that? Well, then that can run, basically runs on humans, right? This goes back to Will's point about mathematics. It's very similar, right? You make a bunch of symbols on the board. Now the symbols, of course, they don't mean anything by themselves. They don't do anything in the universe unless there's humans there that can read them. And it's got to run on the meat machine of the brain. That's how they end up meaning something, right?
That makes sense, yes, in which the brain is a computer.
So no algorithm, no computer exists in the abstract without somebody at least writing it down, describing it, right? What does it mean for? I guess is there just a space of
we can describe something computationally, right? And it becomes a computer. Yes, but the idea of a computer should be, I mean, I'm making an argument here. I'm not really saying everybody feels this way, but the idea of a computer should be regarded as a concrete entity and the program, the abstract entity.
So we're getting into a really interesting thing here among mathematical philosophy of mathematics, of sort of where do numbers live? Because there are certain types of numbers that we actually can't denote. We touched on this last class, and algorithms similarly, right? If we accept that those are numbers, then we accept that these algorithms are real, even if no one writes them down.
So whoever came up with those 7, in some ways, it made them exist by virtue of describing something that gives rise to the idea that there are 7 of them. And that those are still. Did they exist before that mathematician, whoever it was, described them? Well, presumably they did, but. In what way was there something that we could reference as being those things? There was no way, and therefore, what does it even mean to say they? I don't know, to say they existed.
So this is a debate, the biggest debate in the field of philosophy of mathematics. Okay. So if you think, and Will should be interested in this. Will, this is one of my fields. I know you're a mathematician, so I really like philosophy of mathematics. Okay, it's like my thing. So, the Platonists think that there is an absolute objective mind-independent reality to numbers, equations, sets, okay? But then others think they're entirely mind-dependent, the anti-Platonists. And that was where Elon was kind of landing a little bit when he was speculating. And so it gets tricky, right? I mean, this is a whole intriguing arena. That's why philosophers have spent so much time on these issues. But anyway, the thing to remember with respect to the question, what is a computation? I mean, Rachel's point, Elon's point, great points. In addition, though, I think we also have to remember that if we start saying a computer is an algorithm, we arguably are making a category mistake. We're moving from something that we might conceive of initially as concrete, the computer, to something that's abstract. Really, the computer is the thing running the algorithm. Okay, so
what is a Turing machine then? According to that,
Turing machine is
because it has an infinite.
It might be the root. It might be the root of the problem, the conceptual problem, because that was an abstract entity.
Will, did you hear that?
As I can tell, as you point out about the infinite tape.
Well, no one's ever built one, really, right?
What?
But
Yeah,
yeah,
no one ever built a Turing machine. It's like an odd thing. It's not actually a.
no,
So
the idea that the Turing approach is maybe what led us on the wrong path. It's very interesting.
Turing machine is buildable for any given problem because it's initialized with finitely many objects. All you need is to be able to generate another element.
Right. But the point, you know,
Buildable, yeah, you can instantiate it, but
it's not buildable.
yeah, I mean, so it's sort of an idea, an abstract idea that you can instantiate, sort of like an architectural plan.
Yeah.
But I think it's abstract.
But here's what, right. I'd say I'm in support of Susan's position. And as the joke goes, you know, that's fine in practice, but what about the theory? And what it's true, you can build pretty much any, you can build a Turing machine to handle pretty much any problem you can come up with, but not arbitrarily. And the point is that Turing proposed something that is inherently not physically, you know, instantiable, and therefore we would take it out of the realm of grounded and into the realm of abstract. I think, right? Is that sort of a good support for your position? It's inherently, you can't, right? Inherently,
I mean, it's like the number 2.
But it's arbitrarily close to not abstract, right? Because he really was using, again, I come back to this.
Yeah.
He had to use the metaphor, so to speak, of a tape and a control head. And so, by the way, let me just tell everybody about the Turing machine. So, we've had computers of sorts, depending on, forget the definition for a second, but we had complex mechanical devices, things that machines, physical machines, or even abstract machines like mathematics itself, right? What is mathematics? Like I said, it's sort of, it needs a human to run, but it's a set of programs. It's programs for humans, right? It tells us what operation to carry out, and then we do those, you know, and then we get the answer, right? You have these symbolic things that tell us what to do in order to get the answer. And so, at least arithmetic, right? Basically, that's what it is. So we've had computing of sorts for a very long time, long before, you know, before 200 BC was something called the Antikythera mechanism. So I'm sure that wasn't the original name, right? It comes from the word antique. That's probably not what they used to call it when it was, you know, the brand new model.
Actually, it's a really bad name because that just happens to be the name of the Greek island where they found it.
Oh, even worse. Okay, so that's not. Anyway, it has nothing to do with the function of the machine. But it's clearly a complex machine. They've tried to work. They haven't sorted out all of its purpose, but it's able to do pretty complex. I guess you could call them computations. You know, it's having to do with navigation and you know, the constellations, and in order to be able to, you know, do commerce, right? So this really had to be built. The king was like, build this thing that's able to, or there was probably a long lineage of people building machines that could do this kind of navigational trick, so you could figure out where you need to go, and depending on the season and you know, where the stars are. So we've had machines that do complex things. And slide rules are more recent, but it's actually an analog kind of computer. So these things operate based on mechanics. They certainly aren't doing symbolic computing. They're not using electricity. Not that electricity is necessary for symbolic computing, but in any case, they weren't doing symbolic computing. You just use physical rules and the physical properties, like sort of the distance, the physical, you know, actual physical distances between little numbers here, and you just are able to combine those by, you know, sliding one thing over the other, for example, and you're able to get you're able to do complex mathematical operations. So we've had these kinds of things for a long time. I don't know when slide rules were invented. But what we didn't have was sort of programmable machines. And at least as far as I know, as far as history has, I think, been able to show us, is that there aren't general purpose programmable machines. And so programmable machines comes sort of more in the tradition of mathematics, where if you think about, you know, the meat machine, which is us, we've got a bunch of symbols. And you can give me arbitrary symbols. First of all, you could give me mathematical symbols, and I can do a mathematical operation. But you can also give me, you know, regular linguistic symbols, right? Language itself. You can tell a person to do something, and they'll do it, you know, half the time. And so you've got sort of a general purpose system that's able to take in if you give programs and produce some sort of function on the basis of that. So I think we think of digital and symbolic computing becoming more in the tradition of language, because it's really built on this idea of formalisms, things like help me out here, Whitehead and Russell, and what was the The thing that Girdle demolished, real quick, it's a thesis. Anybody help here?
Hilbert.
Is it the church? It's not church turing. What's that?
Hilbert. David Hilbert. That was the guy who wanted to mechanize all of mathematics.
Yes,
Hilbert?
exactly.
No, but it was Hilbert. Right, Hilbert. That's right. Hilbert was the one who actually proposed the challenge to ground all of mathematics in symbolic logic. And so logic's really the precursor.
Yeah, the idea was, can you mechanize the proof process? Can you sort of build a machine that could mechanize
Exactly.
mathematical
Right,
thinking?
now they weren't describing in physical terms, originally. So there are a couple of folks who took on this challenge and they thought they were making really good progress, actually. And then Girdle shows up and says, not only aren't you making good progress, there's no such thing as progress because it's actually undoable. You can't, no matter how long, how you work on it, you will never get there because so give up now, which they did. They promptly did. That's how you know proof is really good. If everybody throws up their hands and says, screw it, right? We're not going to we're never going to get there. It's impossible. So that idea of, sort of symbolic representations of math, but that could be, then you could algorithmicize in a way that's such that if you have the axioms, which you can think of as sort of a program, right? It says that there's different things that combine in certain ways, the plus and the minus, and then that does stuff. And you have these groups and then operations over these symbols, then give you different symbols, and you could kind of define the whole thing. It's going to run, right? But before anybody had ever thought about a computer doing it, or I shouldn't say that, before we are aware of that, in terms of the historical record, that anybody had really thought about physically building such a thing that could do this kind of proofing. The people have proposed it, right? Proposed it symbolically. You come up with a set of operations you write down on a piece of paper as a mathematician. This is how you could or couldn't do it. And Girdle came along and said, you're not going to be able to ever ground mathematics fully in logic, in the sense that you can propose a set of axioms. And there's not, just but some basic things you start off with, like plus is defined, zero is defined. Axioms. I don't want to misspeak because there are mathematicians in the room. But you start with a set of axioms, and then you just have operations that run, and you can from that derive all of the different possible statements, mathematically true statements, based on those axioms. Okay, so that was the program basically. So it's stated that there is some way of fully encapsulating all of it with this finite set of descriptions. So that was the idea. And then Girdle came along and said, no, you just can't. That there's always going to be statements within the system that can't be proven within the system, which means that axioms and plus program, whatever you do here within the system is never going to actually be able to definitively determine what's true within the system. That was Girdle's proof, and it's actually a mathematical proof. In any case, we're left with the idea that we can't fully symbolically represent all of knowledge in a way that runs. And Girdle's the reason why I think it's still taken seriously and important is because again it gets into this question of, can our current implementation of computing, are there things out of reach for it, right? And maybe there's things we can't get our hands on, like consciousness or something like that. That's where Penrose is kind of coming in and saying, yeah, I think Girdle's theorem is basically is consciousness of sorts. It's like they're the same problem in a certain sense. And so so Penrose is saying, no, you're never going to be able to build on what computing is. You're never going to be able to get there. There's something missing.
Quick question. So has computation changed the mind of that type of thinking? Because we have these discussions a lot more because computation have proven to do some pretty amazing things. And it really sounds like sometimes that mathematicians and physicists and everyone wants to stay in their own corner a lot of times when we have these arguments. But I think computation, as much modeling goes on across across every field, there's a lot of modeling that happen that we don't know about, or we do, that there's something that's undeniably about modeling or computation or just the nature of the universe and how we can model certain things that you can't deny. And I think that if they would have had a computation machine that we have now, back when Turing was around, or, a Newman, a von Neumann, it would have been, I think we would have been maybe a further ahead because of the connections they tried to make, more so than just try to stay in their lane. I think a lot of these ideas are the way they are is because I think they tried to make that that connection to other fields. Looking at that complexity in nature.
So wait, hold on. So are you saying that the crosstalk was missing, or are you saying that it was? I'm not. It was a good or bad?
I think if they had the tools that we have now, I think they would. Things would be a little more different. As far as that. I think,
so here's the Girdle. And this is something that gets me very excited, which is the idea that Girdle's theorem really it still depends on a particular instantiation, in some sense.
Natural numbers?
Yes, and some process for treating those natural numbers. It runs on
The successor function?
It runs on symbolic math. Is my point. And we have analog systems that aren't doing symbolic math. And is it true? Does Girdle's theorem even apply in the end? Is self-reference even possible? For example, so the Girdle's theorem, the way it breaks the whole system in a nutshell is it ends up the proof basically depends on asking the system a question about itself, and this leads to paradoxes. For example, if you ask it the question, let's see, how do we do this? It's hard to formulate. If you add, am I lying? And if I'm lying, oh no, I'll never get there. Okay, let me start with the liar's paradox, right? So in language, we can have somebody say, this sentence is false. And Girdle, by the way, actually explicitly mentions the liar's paradox in his thesis. So this sentence is false, right? Is that true or false? Right? It breaks the system, because if it's true, then it's false, right? If the sentence is false, it's true. Well, then that means it's making the point that it's fundamentally true that this sentence is false. So how can that be true, right? Because to be true, it has to be false, right? So it sort of breaks the system. And so it's an English sentence that sort of it breaks the system of English, but we don't worry about that because English works just fine, right? It doesn't matter. Girdle said, okay, I can present to you similar kinds of self-referential statements that have to be sayable within your symbolic system. They're inherently sayable within the symbolic system. And yet the symbolic system will never be able to run over them and be able to conclusively determine one thing or another. It's just outside of the system.
I think there's a really fun kind of point about, all of this we're talking about is when we say like a machine, what I think we really mean is something that's not thinking, something that's not alive. And in a way, we're kind of saying like, can you get something that's clearly not thinking, not conscious, not alive? Can you get that thing to do math, right? So that's sort of was like the original idea.
Yeah, right. And another way of thinking about it, a really dumb way of thinking about it, is can I get somebody else to do this for me? Right? It's just somebody that's not human. Humans are expensive. I mean, it was the original outsourcing, right? The reason why people built computers like that, Approximators, right? Again, it wasn't because they were trying to determine whether, you need a consciousness in order to build AI. They weren't doing abstract stuff. They were trying to solve problems. And they always were, there's always grounded ultimately in a solution that would allow people to determine the conclusion. One definition, I think, and I'll get back to my very first slide. One definition of a computer is a physical system that generates a function. But it has to be physical. Why? Because it's a human tool, right? Maybe computers are inherently human tools. And in that sense, the same, it's very, very convergent with what Will was saying, right? We want it to be a non-alive thing. We want it to we don't have to feed it anyway, we like a human. We don't want to have to train it. We don't want to have to deal with all the crap that humans need in order to solve some problems. We're going to get to solve the problems for us. And it could be even problems that are not human solvable. Like maybe the apothecary was able to do just like a calculator. There's no human being alive who has the time to do 1,000 calculations that a calculator can do very quickly, right? So we don't want to deal with human computers. We don't have other computers that can do this stuff. Let's build a machine that can do it. Do what, you ask? And the answer is give you some mapping between inputs and outputs. And this is my own definition. Again, I'm not stuck to this at all, but I think a computer maybe by definition has to be a physical system, and that's what we think. That's what we think of when we think of computers. We think of something that you can actually build in a physical system. The question is a Turing machine then a computer, right? Because a Turing machine can't actually be built. Instead, you have an approximation of it. And the answer is, who cares, right? Okay, fine. It's not fully a Turing machine, and it can't actually do everything, but it can solve all the problems we want. So I think for the colloquial sense of what people mean by computers, this is much closer. That it's a physical system that generates function. How does it do it? So for example, these logical operations and all this stuff, Wikipedia's definition, I think, doesn't even include natural computing. It doesn't include a water computer. It's not doing logical operations, right? We wouldn't really refer to a water computer. So, well, I don't want to do, I'm not going to do it justice, but,
arithmetic operations, if you will. They're just continuous ones.
well, but then they're not logical operations. So they're arithmetic, but not logical. So logical really does kind of imply.
We can embed logical operations in those.
Of
Yeah,
course you can.
imagine, like,
using logical operations. So that's the thing, right? Maybe I can simulate I can simulate a digital device on an analog system, but that doesn't mean the analog system is digital now. It's still analog. And so it's missing something. I think this.
No, but it can be instructed to carry out digital code with a translation layer, if you will.
Sure. But it also doesn't have to, and therefore, but we still call it a computer. That's my point. I don't think you need to. Sure, you can get it. You can train it like a trained monkey to do something like a Turing machine or some other logical operating machine, symbolic machine. But you could also not. And if you don't, it's still a computer because it still gives you. So what a water computer, or it's really a water integrator, is how they were used. So let's say you want to figure out, how much crops you should plant. You're trying to figure out how much rain there's going to be or something like this. And so you've got a couple of different, I don't know if that's a good actual example, but you've got some sort of sequential data. You have some things that change at a certain rate. Like the temperature is dropping at a certain rate. You've measured that. And the crops are in the past bunch of years, this is how they've grown or something. Terrible example. But you've got a couple of things that vary over time. And you want to kind of combine those these various sources of data that vary over time, and so you could try to do that symbolically, and you'd have to use calculus, and you'd have to try to get actually get the rate of change at a given time, and come up with a dynamical equation that would be able to predict something about where the system is going to end up. Right, so there's dynamical systems, or you can just take some buckets that leak at different rates. Right, I'll fill this one up, and this one fill this one up over here, and this one up over here, and they kind of leak at different rates, and so they're contributing to changes over time. And then you just combine those, right, and you pool them together, and then your aggregate is going to be the various contributions of these different sources of variation over time. Pretty poor explanation of what a water computer is, but here's the thing: there's no symbols in there. There's no calculus in there in any sense that we would ever mean the word. We don't have to do the calculus trick of trying, of squeezing in this symbol that means infinity, whatever the heck that means, and then try to simulate something that's fully continuous. Just use an actual continuous system, an analog system. In this case, water. It's continuous, flowing out of there. It's not. Doesn't have sort of the neat boundaries of digital, and so.
Can I jump in real quick?
You may. There was a big but
Oh, yeah.
Sorry, that was just the of. That depends on what level you're looking at, whether water is or isn't continuous.
I know. And see, when you get down to quantum and all that stuff,
that's the fun thing, is like sort of everything is analog and digital at once.
Exactly.
I think it's sort of a red herring, right? We need to start.
It is, but at some level of explanation, I would say that this is wrong, and it's just, it doesn't capture water computers. It simply doesn't. They're not operating on logical. It's not logical operations in any meaningful sense that people understand them that way. Yes, at the bottom, it's all either maybe it's
not pushing symbols around.
Yeah, it's not switching symbols around. Exactly. So it's not, and so computers are more broadly defined.
Although just you can build a symbolic computer out of water, but that's all.
I know, and I addressed that, and I said, look, you can get a monkey to turn a grinder, and that's great, but it's not about that you can trick it into doing something it's not meant to do, right? It's just, sure, you can simulate digital on analog, but that doesn't make the analog digital.
Would you consider a real computer though, like a traditional, the thing that we're all conferencing on, to match this definition from Wikipedia?
So that's a
Or
great
would that
question.
just a bunch of
That's,
sand and
yes,
metal?
I would, because even though at the bottom it's analog, right? And that was kind of the point I was kind of hinting at before. At the bottom it's analog. It's made out. It's like William said, right? It's made out of stones. It's right. It's operating based on laws of physics. But it's running on physics. It's running on electricity. But that's not the level at which it was designed and in which we understand it as a computer. So this is really just boiled down to semantics for human consumption. Yeah, it surely does.
So then we're back to computer as an abstract concept.
Maybe. Susan, what do you think?
I was thinking about a bunch of things that came out of that conversation so many interesting things. I'm not sure I was thinking about that though. But first of all, somebody makes the point that there's obviously you can sort of roughly map digital to analog, but there's a big issue about fundamental physics and what reality really is, right? And so would this be true? Would the following claim be correct if there's a Planck length, if it turns out that's right, and a Planck's time, like fundamental units, then we're looking at a digital universe.
Yeah, yeah.
Right. Sure, we can still have analog computers, but I mean, ultimately, it's all digital at the bottom.
Right, but
yeah, that's interesting.
Then it's yeah, go.
And the other thing that's really fascinating here, I mean, there's a lot, there's a ton, but I mean, I just want to point out there that I don't think the living, non-living distinction is going to do the job you want for the definition.
Definitely.
Because remember, I mean, this is not, I mean, the formal definitions of life vary, but I mean, like even NASA's official definition of life includes AI. So living, non-living, it's
well, that's cheating. That's saying they're literally synonymous. I mean, then
it's not cheating.
It's tautological.
Substantial.
But it could be that it could be intelligence is only really real intelligence is possible only on biological systems. It could be, I don't know. Get it, Chalmers.
Yeah, no, but we were talking about how to define a computer, and also think about the all the animats that people are building right now. These biological systems which are artificially built in the lab to instantiate computations. Oh, Elon left.
Yeah, like the little brain always.
I'm back.
I was reading about something in the New York Times just this morning. It was like from April 20th of 2020. I'm sorry. I started my day with it. I'm so behind on the news. I'm back a year. But some cellular computer that the New York Times did a piece on. I mean, I don't know why they said it's novel, because it's been going on for a long time. People set up brain cortical tissue, like Thomas DeMars, I think I mentioned him to you before, in the lab, stick it in they've embedded it in deep learning networks.
I want to see this article. I mean, so
the 20th, the one from the 20th of April, the New York Times.
So it's about automata specifically?
Hold on, let me see if I can get my history. I don't know how to do that on iPad. I'm sorry. Can someone Google the 20th of April 2020, like maybe living computers or something?
So you memorized the date?
I remember the date because I'm a geek, but I don't remember I don't know how to use my computer.
That's your address. That's all you do, and then you can always go find it, right? We outsource.
My brain's really weird.
That's great.
But the other thing I wanted to ask you guys about, all of you, I mean, because maybe I'm just not up to date on all this, but when you go back to Girdle's theorem, okay, so the claim there, it's like, any system, I guess it was any logical system suitable for getting any kind of interesting mathematics off the ground had these limitations. And so what I'm wondering though is, can you formalize an analog system so that you can run a Girdle problem on it?
That's what I wanted to say. So Girdle's theorem doesn't apply to analog systems. I'm convinced that it doesn't generalize to analog systems.
Why not? Will, what do you think? Because that could be very, very significant.
I think you can prove it.
The idea of proof doesn't generalize to analog.
What?
It depends on how you define proof.
I think it depends how you define proof.
We need a level. We need a level like.
Can you do that? Can you represent the workings of an analog system in a logical language and then find a Girdle sentence and then go, oops, either this system is contradictory or there's a sentence in there we can't prove.
Yeah, I think that would be awesome to try to build, something like that. I mean, I think just, do we get robots that, hear a tongue twister and then go da, 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 and they just kind of stutter out forever, or do they have some other mechanism? It'd be so cool to kind of figure out. Like, it's awesome to kind of try to break the robots. Like, is there we have this fun idea of just a lethal text in English, right? And so this is like a fun philosophical.
Yeah.
Lethal text. And this is kind of like a Girdle statement for a human being. Right, and this is like a philosophical thing. If I knew one, I certainly wouldn't tell anybody because that would be an ethical thing. But the idea is, and I guess I got to warn you. If I take the idea seriously, I got to warn you even about the idea. It's the idea of like, are there ideas in English or sentences in English that would change, basically would break a human being, right? Like the idea is that the Girdle sentence like breaks this logical, computing system that we call formal math, right? The Girdle sentence just breaks it. What would happen, is there something equivalent for a human being? Some people joke the analogous would be like, is there a song that would get stuck in your head forever and you'd never be able to think of anything else? Right? It might be a different way of thinking about it.
Oh, God.
It's a horrible idea, right? And so is there like an idea that's like so damaging to human consciousness that it would break it?
Probably there are a lot psychologically.
Oh, it's so much we have applied examples. But actually, coming back to this, look, if you had an analog device that could answer it sort of recursively can be, because that means Girdle theorem would be wrong about, because you could then just deploy an analog system within it and get the right answer to that symbolic question. There is no right answer to the question of whether this statement is provable within the system. We don't, or whether, well, we know actually, sorry.
No, it's not.
Sorry, that's the right answer to that. That's right. And we are the ones who have that. And so, right. And that's sort of the idea that we are.
There's nothing special. I don't think it proves what Penrose said. I mean, I can send you responses that suggest, like to Penrose's book, I think it's been responded to in the literature. I mean, I don't think that argument.
He's wrong, by the way. Doesn't mean he's wrong. Just because a lot of people said he was wrong.
All right. We can invite him to talk about it.
Please. Could we please?
Yeah.
I would really appreciate
I mean, I don't know if he'll come. I was supposed to be debating with him in a panel, and then he left. He freaked out.
Oh, okay. Well, tell him.
I don't know what happened. Maybe I wasn't famous enough. I don't know. I was gonna really
initially.
I don't know. But I'm wondering though, it's not true, for example, that an analog system is non-formalizable. I mean, we have continuous math numbers. We have ways of describing mathematically non-discrete systems, right?
Right, but they don't do the same thing. In other words, they can get arbitrarily close to an answer, however, with whatever degree of precision you want, but they don't actually solve it to a continuous degree in the way that an analog system does.
That's true. So that means then, I mean, is it true from that point that therefore a Girdle incompleteness theorem won't apply to that system?
I believe so. But that is a conjecture. But that I think
that is so interesting.
Somebody should work on. But I will tell you this: it doesn't mean that it's going to be translatable back, such that you're going to be able to answer the same questions that are, or it doesn't mean that it can give the answer to within the formalism of the Girdle, whatever the Girdle proof is being. So it's very hard to do the sort of the bridging between an analog and a symbolic system, such that you then say satisfactorily that this thing is doing what this thing can't, because you can't instantiate this problem in the same way. Right? You can't ask it questions about itself. Like, for example, the Girdle proof, it depends on this notion of self-reference within these systems, and you can do that in symbolic systems. There's recursion that allows you to make something that is then within its representation also refers to itself. I don't think in an analog system that would mean anything. And so I don't, it's kind of it's just, you don't have those kinds of problems, but it doesn't mean it's able to solve the problems that a Girdle.
That is so fascinating. I'll have to think about it more.
Yeah.
Can I ask a question here? And I'm sorry if this is like obvious and I'm the only one that's not getting it. But I easily get lost in these semantic debates. So why are we so
We all do.
concerned about why do I care about Gödel's theorem? Like why do I care about
Great
like
question.
can you just ground it for me real quick and try to like bring this home of why
Okay,
we're
I'll
having
tell you
this
one reason why you should potentially care about Girdle's theorem. And that is because it might actually have a lot of practical application in terms of what's really going to be possible with our conceptualization of how to do artificial intelligence. So I think it taken seriously, it's saying that there's, and to take Penrose's idea that it comes back to consciousness. Maybe there's some really fundamental missing piece and that is really, really important. And it's just never going to work, guys. You're trying to train. It's like trying to train an analog system visual, but you're trying to get a system that's just not capable of it. The way you're conceptualizing it is just fundamentally wrong, possibly. So it is a flaw and a fatal flaw, sort of, in a certain conceptualization. In that the system actually definitely breaks. Question is, do we need to worry about it? But it's worth discussing. It's worth discussing because it's said there's a hard limit in our conceptualization of how to do computing. And therefore, maybe we should be aware of that and think about that. That's it.
Okay, so if I'm getting this correct, Gödel's saying that there is limits to mathematics that we can't instantiate, and Penrose is saying that there's limits for instantiating consciousness with the laws of physics. Is that basically like the?
So Girdle doesn't quite say there are problems in mathematics we can't instantiate. Just at a neat level, it's that there are statements in math that are true but unprovable within there's no formal system that will be provable. No formal system. Doesn't matter how rich you make it.
Oh, okay. So the argument then becomes that consciousness may be one of those systems that's not provable.
So that is the conceptual leak that Penrose makes, and many disagree with. I think it's worth reading his book. We should all read it. I would love to read that book.
Okay.
He's actually saying, I think, that consciousness is different than a formal system because we thought of the Girdle theorem. That's the argument.
Yeah, it's not only that we thought of it, but that we can see that it's true.
Yeah, so therefore consciousness is not formalizable. It's not computational. So it's an argument against
computationalism as a theory.
Computationalism.
Yeah.
And it's an argument, to go back to Elon's point, that this is a big ticket issue. It's an argument that AI will never achieve what the human mind can achieve.
Right, and it's not that it may not be just at the edges, right? The argument often I should say often. How often do I get into arguments about Girdle? But you could say that the Girdle's the cases he pointed to, these kind of self-referential statements, are kind of fringe cases. We don't really run into them in everyday life. We don't have to worry about them. They're out there, and we can operate just fine.
No one in the engineering school has ever even heard of it.
Exactly. We can just ignore it safely. We can safely ignore it. And the question is, is that true in the case here of, artificial intelligence, for example? It's maybe, or maybe like something like consciousness. It's like, to get really, there's just a different conceptual level that we're not going to reach that we really want. And it's just going to look like parroting, mimicking or something forever. But then you look at something like GPT-3 and you say, maybe, who cares? Nah, Girdle, right?
Yep. Sorry, I mean to cut you off, Professor. So, but I did anyway. I'm sorry. So,
do it.
So strangely enough, what that means about consciousness is almost saying that, and I think that's the way you guys just described it. It really sounds like some form of bias that he had that he can't deal with. So what that means, what that means is that that consciousness as a perspective as us is sitting in a different location than everything that we're trying to compute and observe. If you take us out of the system, then being consciousness is not a part of that. Like how could you say, okay, if we can't understand consciousness or we can't prove it, but we're conscious of everything around us that is kind of modeled and proven, which, so let's just take our species out of the picture. If you believe that, then any species that we may run into out in the universe, we going to run this test on them to see if they're conscious, like even if they're doing mimic behavior like of us, just because, like, how do we even prove that? Like if you took our consciousness and put it in a robot or something, right? And I say, hey, I'm me. What are you talking about? You're going, no, you're a robot actually. And I look in the mirror and I'm like, I'm sad and disappointed, but that doesn't prove that I don't exist. So that wouldn't even work off planet. Like that idea wouldn't even work off planet, because artificial intelligence could model all those like that the golden record that we sent out many years ago that's flying out in space. An artificial intelligent being gets that record, scans it, okay, and then reinterprets it, goes, yeah, I know exactly what you're talking about. We don't look like that, but hey, yeah. And then we go, it must be real. By what standard? You know what I mean? Just because we've never dealt with it. So I don't know, that idea sounds real. The word is not biased, like he's in self-denial about something, because he knows that it means that he's not truly unique. That's what that's what it almost sounds like. You know what I mean? That's kind of weird. Rachel, I'm glad you asked that question, because now I really understand about what was the argument. That's kind of strange that he would think that. You know what I mean? Because we are unique, but we're not, based on, as much development that we see. There's a lot of similarities in a lot of things in the universe or in nature that we're relatable to. So I just, yeah, that would put consciousness in a different area. I don't know about that. I think that we could probably possibly build it and not build it, but build something that can maybe it emerge. Hell, just like we did. I'm not saying that we're not, I don't know. He sounds like he's in denial about something. It's denial about something, because
okay, let me jump in. So, unique. Who says? You just think. We're talking about consciousness could apply to mice and Drosophila. Who the hell knows?
Yeah,
it's not necessarily like humans are at the center of the universe kind of thing. I think maybe the argument would go something like this. Not Penrose's argument per se. I think he ends up really trying to somehow see it as a corollary or synonymous with Girdle's theorem. But everything we know that has this a certain degree of intelligence. This is how we go. We presume maybe has some degree of this other stuff, and the only counter to that is, well, if we can build something that has a certain degree of intelligence that we think doesn't. But so it would really be an argument against any non-biological intelligence, I guess, maybe, because that's the only thing we know, and we know that that's wrong, right? I guess we could say, no, we've already reached a point where computers surely have surpassed bacteria. Probably, I don't know, C. elegans in terms of intelligence. All right, that's some scale.
Maybe we put a lot of emphasis on the computation part, and it can model or assimilate a lot of our attributes computationally, and then it kind of make you question the universe as far as, is the universe computational? But maybe there is just something else in the room that we're not we're putting too much emphasis maybe on the computational part, and maybe that's why the Turing machine might be a bad example of, or might not be a good framework, to do this,
Exactly. And that was I think in some ways that was kind of my point, that it was leading towards, or trying to, which is that the Turing kind of conceptualization, the symbolic representation, it might get us bogged down in the wrong way of thinking, and maybe that's why AI didn't quite work on some level, because people were too married to that kind of conceptualization. But there are other ways of conceptualizing, not building, but conceptualizing, right? So we have neural networks, for example, which we're not going to have a chance to really talk about today, but they are, I'd say they're the closest we have in some ways to a digital implementation of a system that's inherently non-symbolic. Even though you end up, let's be honest, guys, right? I mean, when you run it, it's certainly not analog. I mean, you have to specify your precision. It's going to run slow if you have a certain degree of precision. You certainly don't have infinite precision, so it's all digital. When we're talking about neural networks, we just have these connected nodes, and we change the weights between nodes, and that's just a number. So we simulate these things, or not simulate them. We run them on computers, and we instantiate them numerically, and so it's very, very much digital in that sense. These things are just represented symbolically based on numbers, and you run mathematical operations, mostly multiplication over it, and then that's how it learns. You basically change the weights, change the numbers, and then that gets better at the function you're trying to approximate. But they're not. They are digital in that sense. But I think, like what we were talking about earlier, is this computer digital or analog? My computers, right? I'd say at a certain level of conceptualization, they're very much digital, of course, because they're running symbolic computer programs. But on the other hand, they're definitely analog, but not at the level at which we really conceptualize it, that abstract level that Susan was talking about, right? The conceptual level, my Mac is just digital for sure. Neural networks, on the other hand, are much closer anyway to something like natural computing, something like water computing. They're in principle, they're kind of analog. You would like to get whatever degree of precision you could. If we could have arbitrary precision, that would be better. Sure, if we could do it without a huge computational cost. And so we really want these things to be continuous, whereas computer programs are inherently just continuous. The symbols are just, they don't have soft edges. Symbol is what it is, and nothing, it doesn't matter. You may draw it with rough edges, you may draw it, but it's still the symbol's an X, and it means what it does in the computational system. Whereas, neural networks, yes, we are limited by the instantiation in digital symbolic computers, but that is an instantiation of a concept that is inherently analog and is continuous. So it's a little closer to other kinds of computing. And that's why, this conjecture we mentioned earlier about Girdle, I don't know that Girdle's theorem has ever been tested on in a neural network, whether neural networks themselves have unsolvable problems that they cannot.
Neural networks aren't consistent.
Are not what?
Consistent.
They run into the same problem.
Well, they don't meet the criteria.
Are they complete and consistent?
I can't hear him, and it's really fascinating. It's so frustrating.
Misha, can you say it a little louder? Sorry.
Well, no, first of all, no natural numbers.
It's worse.
Can you type it in the text?
Or use a different microphone?
They'd be consistent, but not complete.
So to preface it until Misha gets here, so Girdle's theorem basically says that you cannot have a symbolic system that's powerful enough to express the mathematics, arithmetic, I guess we should say.
So first of all, neural networks can't express arithmetic.
Oh wow!
Right, because they have a finite ultimately state, and they're finite, right? They can't express the natural numbers.
In what sense are they finite?
You can't just count or anything like that.
Yeah, they can't count to infinity.
You could get one to count. It depends what you mean. What's the input?
Can't be right.
I don't know what you mean.
You can't represent all numbers.
A recurrent neural network couldn't count. Sure, it could.
Couldn't count infinitely far.
Well, the universe. The universe would end, but in principle, it could.
No, it can't, because it's got a finite size of what it can say.
Well,
I don't understand.
recurrent neural networks are saying,
Basically saying a Turing machine. A Turing machine,
Yeah.
an infinite tape. I'll give this thing infinite inputs, and it'll give me infinite outputs, and it'll count all the numbers.
Yeah, it's an abstraction.
Gosh, it's hard.
Yeah, but the question is, how do you define the numbers that it's counting? Ultimately, a Turing machine cannot compute a Girdle statement, if you will.
Well, you define them using the resources of mathematics, weights and whatnot.
Of which there's finitely many, and it's pre-specified how many.
You're saying neural networks are inherently finite.
In a sense, yeah.
Yeah, it is. It's a set of weights. I mean, any given neural network. Okay. But can we
That's just math.
have a universal neural network? Can we have a universal neural network? I don't know. That's, gosh.
I think the
inputs and outputs, it can learn it. So, and they're Turing complete. They're supposed to be Turing complete. Will always says that there's a proof that with recurrence and what else?
neural networks Turing complete.
Yeah, neural networks are Turing
they're
complete.
complete.
That means they can solve any problem a Turing machine can solve. That means they can.
And Turing machines can't solve this
They're
problem.
Turing equivalent.
So there's this
Robert.
proof for universal function approximators.
Yes.
There is a proof for that. I mean, it's well known in neural networks.
Approximators. Right.
Approximators, but of course we live in a finite world, so they cannot kind of get the precise thing. They have to approximate it.
Does that mean we can conceptually then
you can get
Ultimately,
arbitrary
that's not sufficient for Girdle's theorem, though.
wait, sorry, what did you say, Misha?
You can get arbitrary close to any computable function, but you cannot get not always at least the precise one, because then you would need time to run in a complete implementation.
Emphasis on arbitrarily close to a computable function.
A computable function, of course, exactly. If it's non-computable, then
These things aren't computable.
Well, if it's non-computable, then you're screwed.
generally the case for any class of computers then. So, okay, I guess, but the point is that neural networks then they don't solve the problem of getting out of Girdle's bind.
So ultimately, Girdle's bind doesn't apply as long as you don't deal with infinite things. All right, as long as you've got a finite series of statements. If you can have infinite language, then Girdle's theorem applies. But if you can't, then I don't think it becomes an issue. But I might be wrong there. Someone could fill me in.
Well, in any case, I still are neural networks digital or analog conceptually?
There's both.
They're both.
No, there are both. There's both There's both kinds.
But as conceptualized, they're.
Well, there's both. There's analog neural networks, which is not typically what we talk about. The neural networks we typically talk about are sort of.
Depends, right? I mean, the brain might be an analog neural network.
Well, I mean, like when they in the field of deep learning,
I know.
not doing analog neural networks.
Right. But again, it's just a limitation on an instantiation of it. But conceptually, or whatever, like if we could do it, if we can build one, but yeah, again, you run into problems, right? If you have to build them on limited, digital resources, then you really are limited, right? I guess that's a very practical way of putting the question, and we've talked about this before. I think even in this class, of whether there's something about analog systems and the continuousness of them that is essential in some ways.
Well, I think we definitely know that is going to be the case, especially with power consumption, right? So there's certain and sort of simplicity of the circuits, right? So Turing showed that we can do anything with a Turing machine or a digital computer in theory, but
Right.
sort of in practice, when we have a limited number of calories and a limited number of minutes to do something, we're going to have to rely on analog.
Right. So at a very practical, for sure.
And to go back to the Girdle thing, which I think was really, really intriguing because it suggested maybe there could be a class of analog computers which could somehow outthink digital ones, if you will. I'm not sure if we could even call them computers, but that's another debate. or that there was something special about us. I mean, the chat has been really interesting because Will reminds us that there was classically a general purpose analog computer developed by Claude Shannon, right? And it looks to be Turing equivalent, right?
Yeah.
Okay, so then the Girdle theorem thing, I mean, it should be the case then that the Girdle theorem could apply to it, because you would just, I mean, this could be so wrong. Just shoot me down quick. But I mean, if it's Turing equivalent, wouldn't you be able to put the Girdle theorem to the analog computer and just say, tough shit, you're dumb.
I think that would really be awesome to kind of figure that kind of detail out. One thing that's kind of you'll hear me talk about this a lot is how frustrating it is to get these things. So here we are from 1941, Claude Shannon, Mathematical Theory of Differential Analyzer, and $10 to anybody who can get me that actual PDF, because right, that's just so crazy about how this community works, and it's just too important to make that thing available, right?
You need the paper? I can get it. I'm at the Library of Congress.
Okay,
what
perfect.
paper do you need?
Okay, perfect. I'll send you the link.
Okay.
It's in the journal. We should just FAU just doesn't get this particular journal.
No problem. I'm at the Library of Congress.
Oh, that's amazing. Awesome.
So there's just to quick paraphrase. There's a theory of sort of scientific dissemination that what we end up seeing is that's the B list, because the really good stuff, the people who are who ultimately have vetting and control will go and snatch it up. And there are probably all kinds of amazing scientific ideas that are not disseminated to the public, and this might be one. Analog computers may have gone underground very quickly because they were so damn good.
I can get stuff. I can get white papers. Just let me know whenever you need something.
I linked that article in the chat. It's actually was on BOOK.
How do I capture the chat, by the way?
After
I'm
class
putting
ends,
it-
I'm gonna.
No, I want to be able to disseminate it, because there's a lot of good.
It's on it. I'm already typing it in an announcement. As soon as we end, I'll publish the announcement.
God, you're amazing.
You're awesome. Thank you.
Thanks, guys.
Well, I mean, we covered so much cool today. I'm part of so many debates, like what is a computation? What is a computer? I mean, this is so big ticket. To just give you a sense, like if you look out there in the physics pop science book industry, like you get people like Max Tegmark. I don't know how many people read his book, The Mathematical Universe. He thinks the whole universe is an equation. And I told him, I'm like, Max, that's a category mistake.
An equation is something you write on a
check. This is a concrete entity.
Stand up.
And Seth Lloyd, do you guys know Seth Lloyd over at MIT?
Oh, yeah.
The universe, he's great. He's there. I mean, these guys are all my buddies. I love them. The universe is a quantum computer.
Yeah, I kind of agree with you that these are like, how is that even meaningful in a sense, right?
It's not.
Right? Like we can talk about what a computer is, but to say the whole universe is or isn't a computer, I'm not sure if those sort of questions are well defined.
Well, look, the upshot from today was that a lot of us were okay with what's called pan-computationalism, right? Elon and Rachel both supported that, and I think, hey, why not? As long as we don't know what we're talking about, a rock can be a computer, and if that's true, the universe could be a quantum computer.
And it's one of these things that all models are wrong. Can we extract utility from thinking about rocks as computers or brains as computers, or is it holding us back because there's some other way we should be thinking about it?
Exactly, and that's why I think this, it's a useful exercise, because you make choices about which direction to pursue. You only, as a species, we may only get one good shot. Who the hell knows?
Is everything in the universe formalizable? That's probably one of the deepest questions around. I mean, formalizable in principle, obviously.
Right. Misha was you were trying to say something, I'm sure. I heard it, I think.
I think might be on mute, Misha.
Will, insert AV AI joke here.
We will never solve AI if we can't solve AV.
Audio visual guys? I'm sure.
I know, right? Here we are trying to build HEI.
Right, like a superhuman intelligence is going to be much easier than like a fully functioning Zoom system.
Exactly.
Did you see that lawyer who his kid changed his Zoom screen to a cat and he went into a legal hearing and he couldn't fix it?
It was hilarious.
Hilarious.
Yeah,
I want my Zoom
Digital
kid.
gold.
It was so great. It was like this cat with crazy eyes. And he's like, really, I'm a human.
Although to hijack the joke and turn it serious, like maybe AI should be handling our AV, right? I mean, if you have a cat picture and you lose when you're looking at it, and your computer should be able to look at his camera and notice that you're scrambling and it's doing something wrong, right? Any child could have guessed what the problem was there. Why can't his computer guess what the problem is there? And then there are many instances where this kind of thing happens, where you just kind of wish AI was already good enough to do it. It almost is already.
I think there's also like a fun or like a good distinction we need to think about with computing versus communication. And the way I like to think about this is if you were to hand, a regular person on the street, particularly a young person, and you were to give them like a really awesome computer, right? Like tons of memory, the best chip they've ever seen, but you tell them it cannot and will not get on the internet. Do they even want it? Right? You want that yourself, right? And I think as scientific researchers, we might want one for ourselves to do an experiment or something. But if in general, if it doesn't get on the internet, it's broken, right? So it's funny. We almost have to separate what we intuitively think about what a computer is for. Elon, you had this definition up there. It'd be great. Ask your kids later, Elon, to give them, because for them, like a computer is this thing you have that lets you get to work, it lets you send messages, it lets you see your friends, it lets you play games, it lets you see.
But all of those are actually consistent with that definition.
Oh yeah, absolutely, absolutely. And I just mean I guess what we mean to say is when we say computer, like not the internet. And that's because the internet adds this whole other fun layer of like, well, wait, what does that mean? Now these things are talking to each other and stuff. But it's just, I like to think of this, what a computer was before they had the internet. It's just an interesting kind of idea.
That's right.
As we're talking about kids, my 12-year-old daughter just made a great point. She said that the universe is the law of conservation basically says there's nothing created or destroyed. So therefore, a computer can have input output because you can input anything. The universe can't be a computer because you can't input anything, but you can output anything because it's the law of conservation. So that was her point.
If the law of
right?
conservation for the universe also doesn't exist.
First of all, why the hell does my 12-year-old not come in here and make a statement like that? That's amazing.
That's a smart kid to be thinking about all this.
Saying there can't be, it can't be, because that would be destruction of information in a sense, or something. It's a conservation of matter and conservation of information.
The law of conservation is kind of an overstatement.
How so?
Do we really know that one's true?
About matter?
Yeah.
No. We have black holes. We don't know what happens.
But if that's the case, then we don't know anything about anything.
Yeah, there's some really good, interesting
but
questions about information, and is information conserved, right?
And black holes are at the nexus of conservation of matter and conservation of information. It's the same thing, right? You never could find out after it goes to the event horizon. You can never find out what happened to it. It's inherently impossible. It's beyond. That is why there's the event horizon, right? So it's a loss of information, but it is also a loss of matter. Potentially, we don't know, right?
So Susan, you're going to have to get Scott Aronson to come give a talk, because he's like the world expert on some of this kind of stuff.
Oh, I didn't know Scott worked on black holes, but he's a quantum computation world expert.
Yeah, and what's such a kind of a fun twist of like science, he does like all this like looking at how problems like exactly quantum computations. And there's this cool problem called the firewall paradox that astrophysicists were looking at for black holes. And he's now like on these papers because they're invoking some of these computational complexity arguments to sort of explain why the black holes are the way they are. And it's just so cool.
That's so cool. So is he arguing that like for a new solution? I was just reading that there's some claim that information is conserved inside a black hole.
Yeah, just the sort of a new approach to physics in a sense. Like what are the sort of the axioms and assumptions and the base ideas, and then we build everything on top of that. And I think kind of the argument is this notion of computational complexity and computational resources. They have to invoke those ideas to explain this data so far, what they observed from black holes.
Oh, if you see anything on that, I'd love to see it.
Absolutely. Yeah, I just posted one of Scott's talk, an older one. Let me find the newer one. Yeah, hang on.
Well, by the way, Scott ripped IIT to shreds. If anybody wants to see the takedown, I can send it.
Please do. That would be awesome.
Oh my God.
Yeah.
Yeah,
Game, set, match.
oh, it was so embarrassing for Tononi.
Wow.
Yeah, it's like, oh, well, a CD turns out to have a shit ton of phi. Excuse my language.
Get it. Got it. Right. And since the whole thing's built on intuition pumps, then if your intuition breaks, then it's not even doing that. Forget it.
Well, Scott did the math, and he's like, a compact disc has a lot of phi in it, and so Tononi just said, well, it's conscious it's like in a rich way. It's conscious.
That's the thing. And the whole thing's built on this premise that we have, which you could definitely debate altogether, right? I know that I'm more conscious than a person in a coma or somebody or an ant, right? And then we start with that as almost a set of axioms as to what has certain levels of consciousness. Now you could debate that, but if you break that intuition and you want to start telling me that it's all built on intuition in the first place. And if you give me a proof case where your intuition is that a CD is not, you can't then say, I'm going to follow by theory. Then you look like an idiot.
But I think this also exposes like a greater flaw with what we call information theory and just that, Shannon's classic definition. And Shannon wanted to call it communication theory. And that's really what he came up with and what we have. It's about communication. I don't think we've really developed a full information theory in terms of what we intuitively mean by information, because by just like with the other thing with Shannon's classical definition, like a broken analog television that's just showing you the white noise, that has by definition like a ton of information, but no little kid would watch that for even 2 minutes. So it's somehow missing what we think of as information.
Yeah, I mean, I deal with this all the time. I mean, it's so frustrating. Like in so many cool fields like biology, physics, philosophy, computer science, AI, cog sci, there's this idea that information underlies everything. Right? It's right up there with the appeal to pan-computationalism, and I think they might be related. And I don't have a problem again with the pan-computationalism idea, but there's this idea that everything is information.
It from bit, right?
It's from bit. And I'm writing a book called From Bio to Bit, by the way. Yeah.
Sounds like we should talk about some stuff.
I mean, see, the thing about it from bit is that a bit is abstract. And so again, it goes from abstract to concrete, and it just doesn't make sense. If the universe is Shannon information, the universe then is a mathematical entity.
I have to come back to this abstract. Nothing's abstract about a bit. It's something's on or off. What does that mean? Something has a certain state. Well, you have to define it. It always has to be grounded somehow in something that draws on our physical intuitions. It's never. What does it mean? Something has a state. Not only physical things have states. So they can be lit up or not lit up, filled with air or not filled with air, whatever. But there's no such thing as bits without its. There is no bits without.
Sure, they're complementary, but let me just put it this way.
I wasn't debating anything you said. I was going back to.
Yeah, no, I understand. Maybe the way I should have phrased it is that information theory, being a branch of physics, was framed using the resources of mathematics. And it's information itself was understood in an abstract mathematical sense. There's no information in the universe. It's a way of describing a state. And so the fundamental layer of reality, contra physicists like Carlo Rovelli, who are writing all these great theories of quantum gravity, it can't be information. There has to be something beneath it. Look, who was it? Stephen Hawking, the late Stephen Hawking. He said, what is it that breathes fire into the equations?
Exactly.
That's what we need to figure out. And that's going to be something like matter or energy. It's got to be, right? Something real.
Those
not
are
some abstract representation.
Those are mathematical.
Equally abstract.
What?
Matter and energy are equally abstract.
Equally abstract.
How we talk about them.
In fact, they are abstract words for really mathematical concepts in physics.
That's true, but I mean, everything is describable mathematically. That's the beauty of physics. The formalizability. But
the gram is no more real than the bit, though. A gram of sand is no more real than a bit of information.
You might want to, I mean, maybe this is fields that we're talking about rather than matter, but that's different. It has I mean, it's not, is it all just mathematics, or is there some energy or something that is a concrete realization that lies beneath the equations? Like, I don't see how to make sense of the universe if it's all just mathematical equations.
It's certainly not mathematical
equations. All of mathematics has been gleaned by monitoring physics and saying, oh, there's a relation between these two.
And just a way of communicating, frankly, to ourselves and to other brains. That's really what math is. There's no way. That's why it doesn't even make to say that the universe is made of equations or made of bits. In and of itself, those are our own thought. You know, those are our own symbolic tools for modeling whatever the hell physics really is.
What's really interesting is I mean, no matter where you come down on this issue, you can see that it's a philosophical question and that it is currently underlying a lot of work in biology and physics.
Yes, sir.
It's crazy.
Well, we do need to grapple with this a little bit. I think people need to be aware that these conversations exist, including myself. You know, this is very rich, and it's not just some curiosity on itself. People are spending a lot of money, time, and resources to try to get at some questions.
It's super weird.
All right, and it's 3:45, and I have to take a flight, so I'm going to leave.
Oh, have a good time.
Thank you. Should I stop recording? I was recording this. I don't know. Somebody else can stop recording when I leave.
Wait, before you go, Subodhana and I wanted to say we had an idea of creating essentially an experiment of this IIT. Can we create a system that maximizes over time this phi and shows that it doesn't do anything?
There's
got to be a set of rules that maximize phi.
You evolve it to, oh, that's awesome.
Exactly, evolve it to maximize phi. If we can reasonably measure it, which I know it's computationally infeasible.
That's a great idea. It sounds like a really cool idea. I don't know much about phi, but it sounds like fun.
Hey, Elon, where do these recordings go?
So I have not recorded too many of these classes. I don't know if I recorded any, maybe one other.
Why not?
Because I forgot every time. And, you know, it's because we kind of glide into class instead of being like class now started. Instead, we're having a conversation, and then it becomes the conversation, and I never think like now class starts, so it doesn't occur to me. But I did record this one, and I will post it on the Canvas, or I could put it on our GitHub. Let's do the Canvas, the GitHub for the other course. I'll put it on Canvas for now, and we can do with it as we want.
And somebody was asking about the phi maximizer.
Yeah,
look at Scott Aronson's grid for ideas, because the grid does nothing. Okay, you'll see it on the chat. I suggested how to.
But it's just the grid has high. Doesn't do anything.
Someone just copy and paste this chat into wherever you take this video.
Sorry?
Can someone copy and paste this chat to wherever you take this video?
Oh, that'd be great. Yeah, Rachel's doing
it. Is someone sending this chat around to the group today? Because it'd be good, because I want to read more about.
It's an announcement. It's in the.
Thank you.
Thank you.
Thank you very much, Rachel, for all that. And for your earlier lecture at noon. That was, I jumped in late, but it was really interesting.
Oh, thank you.
Yeah,
I love Unity stuff. So if anyone ever wants to do Unity stuff, just email me. I'll totally do it.
Programming has got much better, much more user-friendly.
Yeah, absolutely.
It's amazing.
Isn't it?
Well, I'm leaving, but everybody else.
Okay, bye, everybody. I'm gonna run too. Gotta take the dog out.
Take care, everybody.
Okay, bye.
Yep. Leaving too. Bye.